my name is Sarah Koep, and I'm a junior in Civil and Environmental Engineering at North Dakota State University. I've been a member of the Nano and Virology Research Group at the university since 2017, and the research that I'll be presenting today is on the modification of granular activated carbon using natural citric acid from Citrus aurantifolia for enhanced fluoride removal from drinking water. And as I begin my presentation today, I would just like to say that you're more than welcome to interrupt me at any time if there are any sound or connection issues. With that being said, I will begin with an introduction to my area of research. Excess fluoride in drinking water is a global issue that has detrimental effects on human health. Fluoride is widely distributed in the geological environment. Rocks containing fluoride slowly dissolve and release fluorine. Rocks containing fluorine slowly dissolve and release fluoride into groundwater, and that is what contributes to its natural presence in drinking water. Additionally, fluoride enters drinking water sources through agricultural and industrial pollution. The World Health Organization's fluoride guideline of 1.5 milligrams per liter is exceeded in drinking water sources used by over 200 million people worldwide. So you can see why this is an issue of great concern. Regions that are greatly affected by this include South America, Central Africa, China, and India. And you can see this in the map. The larger that the blue circle is, the greater that the area is affected by high levels of fluoride. The ingestion of small amounts of fluoride is actually beneficial and necessary for bone mineralization and dental enamel formation. However, excess fluoride in drinking water sources causes several health problems of great concern, particularly fluorosis, which is characterized by mottling of teeth, brittle bones, and sometimes brain damage. Additionally, osteoporosis, arthritis, and cancer can develop. Now we'll move on to the objectives of this research. Since a significant portion of those affected by fluoride contamination live in rural areas, it's necessary to develop defluoridation techniques that are both inexpensive and feasible to be used in rural areas. Additionally, my research aims to find a natural method to remove fluoride for the benefit of human health and the environment. Now we will talk about the approach that I took for this research. The first step in the research process was determining the method for fluoride removal. The use of adsorption technology has shown potential for this due to the relatively low cost and simplicity of its implementation. This process involves the passage of water through a contact bed, where fluoride is removed by ion exchange or surface chemical reactions. And the diagram on this slide shows the difference between adsorption and absorption. Adsorption is when it actually is sticking to the surface, not being absorbed into the material. This figure shows the steps in this research process, each of which I will be explaining in the following slides. We begin by choosing the proper material to use. Activated carbon is commonly used for absorbent due to its high porosity, large surface area, and high catalytic activity. Modification of the activated carbon surface has shown to improve fluoride absorption. However, most modification methods remain too costly and impractical for applications in the rural areas that we are considering. Surface modification, on the other hand, shows that it can improve this removal. After selecting the material, the surface modifier was then chosen. Past research has shown that modifying the surface of granular activated carbon with citric acid improves the fluoride absorption. This is done through the introduction of additional carboxyl groups on the material. To find a more natural source of citric acid, I considered citrus fruits, and I found that the concentration of citric acid in lime fruit is very close to the optimum concentration determined in citric acid modification studies. Therefore, for this study, I consider the simple and inexpensive modification using lime juice. And what I call this material is LGAC, lime granular activated carbon. To prepare the LGAC, first lime juice was extracted, and this was then filtered to remove any extra particles or pulp. Its citric acid concentration was determined by titration so that it would be approximately equal to that was used in the citric acid experiments. 25 milliliters of the lime was then added to 4 grams of dry granular activated carbon, mixed at a low speed for 45 minutes, and placed in an oven for 24 hours at a temperature of 101 degrees Celsius. Next, the substance was washed thoroughly with deionized water and placed in the oven for another 24 hours. Once it was prepared, the LGAC was used for several studies to determine its removal efficiency under various conditions. Triplicate samples were prepared in glass vials containing 400 milligrams of LGAC and 20 milliliters of the solution being used. These were placed in an end-over-end shaker for 24 hours, with the exception of samples that were used to determine the effect of contact time. The amount of fluoride removed by the LGAC was determined using a spectrophotometer and calibration curve. Now we'll move on to the results of these studies. To determine the effect of contact time, samples containing a 10 parts per million fluoride concentration solution were placed in an end-over-end shaker for 15 minutes, 30 minutes, 1 hour, 2 hours, and 4 hours. A study was conducted to determine the effect of pH using pH values of 2, 4, 6, 8, and 10. The effect of fluoride concentration, which is what's shown in these graphs on the screen, was also studied using solutions with fluoride concentrations of 5, 10, and 20, and shown here are the concentrations of 5 and 20. The results of this can be seen here. The CAGAC removed 83% at 5 ppm, whereas the LGAC removed 88%. And then at 20 ppm, the CAGAC removed 74% and the LGAC removed 83%. And the reason that I have the data for this is because there was another person in my research group who was doing this CAGAC research, so it's kind of nice to have that comparison to look at.
2 minutes.
This figure shows the absorption capacity of LGAC in comparison to the CAGAC and the unmodified GAC also. From this, you can see that the absorption capacity of the GAC was only 0.88 milligrams per gram, whereas for the CAGAC, it was 1.65, and the LGAC was slightly less, but still comparable at 1.63 milligrams per gram. Ionic strength and interference studies also took place. Since various ions are typically present along with fluoride in the water being treated and are in competition with the fluoride for active absorption sites, decreasing the LGAC's absorption of fluoride is necessary to look into this interference. To determine this, solutions containing chloride, sulfate, bicarbonate, nitrate, and phosphate were prepared. The interference of each was tested separately. As shown in the figure, there was relatively no interference at lower concentrations, and the higher concentrations that were tested, while they had more interference, they typically aren't present in groundwater, so this isn't too much of a concern. This figure shows the effect of pH on the fluoride removal. You can see by looking at this that between the pH of 4 and 6 is where the most removal occurred, and there's very poor removal at concentrations of 10 and above. Now we'll move on to conclusions of this research. The fluoride removal efficiency of the LGAC was greater than 70%, which is greater than many technologies.
Time? Okay. So there's 10 minutes and time for questions.
Okay.
What is the normal pH of most groundwaters in the areas that you're looking at?
It's typically anywhere from 5 to 7. But another thing to consider is that with adding an acid such as the citric acid, it could decrease the pH slightly.
So go ahead, Jonna.
Is the thought that this is a simple enough additive that would be easily and cheaply enough done for these countries?
Yes, that is a thought. And also a lot of these countries do have citrus fruits readily available. They have the right conditions for growing them.
But you'd have to figure out a way to make it more industrialized because they're not going to be able to do the heating, cooling, washing, that whole process you showed.
Right.
You have to figure out how to industrialize that. Okay.
We were trying to find a method that didn't involve a lot of chemicals that might not be available or maybe toxic to the user.
It's kind of a random question, but has anyone looked at what tasted the flavor of the water? Did it change and taste more lime flavored after doing this treatment? Even just like filtered water?
Sure. I guess we have not looked into that research yet, but that would be interesting to see.